Hello, and welcome to our project presentation on cache optimization for SAT solvers. Let's introduce the topic in a line. SAT is an NP-complete problem, and a key challenge with SAT solvers is that they often rely heavily on cache memory to perform efficiently. Cache memory is a type of high-speed memory that stores frequently accessed data closer to the processor, and that reduces the need for slower main memory accesses. We tried a few things in this project, some useful and some not, but we still gained valuable insights through our research. We will present our findings here.
So here are the things we experimented with. First, we varied the number of ways, also called associativity, and observed the effects and conditions if the size is constant, and the other where we can keep the number of sets as constant, in which case the cache size will vary. Also, we experimented with different cache sizes and the different possible combinations in the three caches. Also, we experimented with the different functions where latency is varied with the total size, one's linear and one's logarithmic. Also, an important parameter which can affect the performance is the block size for the cache, and it was varied with different proportionality with sets and number of ways. The three inclusion policies were also tested: inclusive, where the higher level caches are subsets of the lower level caches; exclusive, where one element is present in maximum one cache; and the default non-inclusive, non-exclusive policy, which in some ways behaves like the inclusive and in some ways behaves like the exclusive policy. So we also experimented with different cache replacement policies. The least recently used, as suggested by the name, removes the element which was accessed the earliest, and the most recently used, which was accessed the latest, and the random, which chooses an element at random, and the basic implementation of the re-reference interval prediction type of replacement policy, that is the static RRIP. So as the total number of possible combinations can be in the 100, as we are tweaking a lot of parameters and policies, we classified the optimizations into three major categories and experimented with each of them individually. We test one thing at a time while keeping others at the default value, and we choose the best set of values among all the different categories for the maximum performance, which should not give the best possible performance, but give us a close enough approximation in a limited constraint of time. Okay, so now we move on to the results and observations section for all the categories. First, we see the result of using different replacement and inclusion policies. So in both the canonical traces, as we can see, similar results are observed, as in the exclusive inclusion policy performs the worst in all the replacement policies, and different replacement policies have different results. In the case of exclusive policy and in the case of inclusive and 9, they perform almost the same. We observe slightly different things in the KISAT trace, where the replacement policy ship performs much better, which was one of the worst performers in the canonical trace, and the most recently used replacement policy performs the worst, and the trend of the inclusion policy remains the same. So from this we can infer that the dynamic RRIP is a consistent replacement policy, but the ship replacement policy performs worse in canonical and better in KISAT. Also, it is observed that the inclusion policy, the exclusive inclusion policy, gives worse results, although we observed significantly higher hit rates, but the effect of the increased latency outweighed it and the net performance was degraded.
So now let's come to some interesting stuff. Let's talk about changing the structure of the cache. There is a number of ways, number of sets, size of the cache, things like that. So as you can see, the first thing we did was we took a constant cache size and we changed the associativity of the LLC cache. So keeping constant cache size means that we decrease the set as number of sets as we increase the associativity, which is the number of ways. As you can see, there are small increments as we increase the associativity, but the increment is significantly more in the LLC, as can be seen in the scale. After that, we took a variable cache size. That means we kept the number of sets constant and allowed for the expansion of the memory as the cache associativity increased. Similarly, again, you can see that LLC has more impact than L2C, You can also see that the scale for these graphs is much larger than the scale for the previous graph. So here's a comparison. So as I explained earlier as well, you can see that LLC has a much more significant impact than L2C. For example, L2C's impact is barely visible over here. And in constant size versus variable size has significantly more impact. So when sets are constant, there is significantly more increment in the IPC. So what are the reasons for this? It's pretty straightforward. For LLC versus L2C, a good LLC only prevents costly memory accesses, while a good L2C only prevents LLC accesses, which are not as costly. So LLC improvements are better. Secondly, why constant size is worse is because when we have variable size, we allow for the cache itself to grow and more memory to be stored in the cache, which decreases the miss rate. Okay. Then we varied the number of sets. Again, we had to do this for different caches. So for L1 caches and L2C caches, we have done it here. As you can see, L2C caches has a greater impact. The reasons are similar. Here's a comparative. So LLC cache has significantly more increment compared to L1 and L2. Then something we haven't considered yet. When we vary the size of the cache, we also should vary the latency. That is, the latency is hard-coded number in the simulator. And when the cache size gets larger, we actually want to change this number, so that we can simulate the larger cache size, which will actually be slower. But we couldn't actually figure out a good function for the latency for how the latency should vary. So what we did was we took some guesses. Mostly, we thought that it could either be a linear or a logarithmic function. Here are the so it assumed took some lines with certain slopes, and we took a logarithmic function. So the first plot shows you the functions themselves. So this is the function of this is the latency as a function of your cache size, and the second graph actually shows how the IPC varies for each of these functions. As you can see, for higher slopes, the latency increases quickly with cache size, which causes larger caches to actually be significantly slower and discourages large caches. This can be seen in the orange line here. Similarly, in the purple line, in the brown line rather, you can actually see that low caches actually encourage large cache sizes, because we've already shown that large cache sizes are good because they store more data. But at the same time, low slope will imply that the latency doesn't increase either, and hence we can conclude. We also can see from this graph that there is a critical slope above and below which you can actually decide which size of cache is suitable for your own system and your own problem.
Now we can move on and analyze what happens when we change the size of each block. Okay, so when we do so, we have two options. One where we keep the size of the cache constant. For this, we have tested both the ways. One where we keep the adjust the number of ways to keep the size constant, and one where we do it with sets. And the second would be variable cache size, which increases proportional to the block size when sets and ways are held constant. Okay, and since we are trying to deal with variations in block size only, we will keep the structure within the L1, L2, and LLC cache similar to what it was in the original Samsung implementation. That is, when decreasing or increasing the number of sets, we'll do it for all the three caches with the same factor. And also for this part, we have tried it out on all the three traces: Cadical 134B, Cadical 1227B, and KISSAT. And we have skipped Cadical 113B because it cannot be run on 30 million warm-up and test instructions, and which would change the amount of cache it requires, and it will not be suitable for comparison with other traces, since it requires lesser cache when tested on fewer instructions, obviously. So yeah, for the first case, here we vary the number of ways to keep the size constant. And here we have a beautiful observation where IPC first increases and then decreases, giving us a maxima at 256. The change from the base case is quite significant. Base case is 64, as was in the original Samsung implementation. The increase is quite significant, 5 to 15%. And also the block size of 128 deserves an honorable mention here, especially because it performs slightly better in the case of Cadical 134B. Okay, moving on. Next we vary the number of sets to keep the cache size constant, and there is nothing much to say here. The trends are pretty much the same as the previous case, and we tried it out for two values of number of ways. Both give the same trend for the validating our observation. So here 256 best with around 5 to 15% increment, and 128 again is reasonably close. Lastly, we see what happens when we change the block size along with keeping the number of sets and ways constant. So why are we doing this? So first of all, we just want to retest our claim that increasing the cache size would increase the performance even when done with the block size. And also there is one factor fighting against that speculation, and that would be the latency involved in copying all the data from DRAM into the cache, because now we are moving more data on each request, and the CPU does not need the extra data all of the time. So that might decrease our performance, and that's exactly what we observe in the Cadical 134B. The 512 block size performs worse than 256. Also, you can note that in Cadical 120 1227B, the increase in performance from 256 to 512 isn't as good as in the case of KISSAT. So that tells you that 512 may or may not perform better than 256. So in conclusion, we can say that the block size of 256 would be our safest bet. Block size of 128 also performs good in most cases, especially when the cache size is held constant, and it is worth giving a chance as those in those cases. And block size of 512 might yield significant increase if we allow the cache to expand as well.
After all is said and done, these are the IPCs we were able to get after choosing the best in all categories. In Cadical, we used only a 4 times cache because the 4 times and 8 times had similar timings. But in KISSAT, the 8 times was significantly better, hence we actually went ahead and used the 8 times cache option. So there you are. Thank you.